So in this video, I'm going to compare the Frequentist P value with Bayesian posterior. And in many ways, this isn't really a comparison between Frequentism and Bayesianism in general, but rather a comparison between p-values and posteriors. Although, having said that, one of the initial comparisons is in fact going to be generalizable, and that is that the Frequentists give us the probability of the data conditional upon the parameters, whereas the Bayesians give us the probability of the parameters conditional upon the data. To illustrate that, we're going to use the example of the IQ of the IB students. And just some notation, the parameter that we're going to be dealing with is the mean IQ of the IB students. When we do the Frequentist approach, I'll tend to use the symbol mu, whereas with the Bayesian approach, I'll use the word mu. These two things mean exactly the same thing, the mean IQ of the IB students. It's just that in doing math, we tend to use symbols, but when I write the RunJags code, I need words, and the word I'm going to use is mu. Irrespective of whether we're taking the Bayesian or the Frequentist approach, there are some things that are going to be common to both. The first is that research that's funding this was based on a grant proposal that had as its research hypothesis the notion that the IQ of the IB students was greater than 100. We assumed that the IQ of IB students is going to be normally distributed with some mean, and that's what we're interested in. We're trying to draw inferences about this mean that can be represented in either one of those two ways, but we're going to assume that IQ is normally distributed with standard deviation 15. We've been doing IQ tests for a long period of time, so we have a pretty good idea what this number is. By assuming that the standard deviation is 15, I can use a normal distribution rather than a t-distribution. The data consisted of a sample of size 9. Those are the IQ values. The overall mean of those 9 values was 111. So, going on to compare Frequentism with Bayesianism. Again, the whole idea is that the Frequentist gives us the probability of the data conditional upon the parameter, in this case mu. Where does that mu come from? The mu here is going to be 100. This is the null hypothesis. So what the Frequentist does is that if the research hypothesis is that the IQ is greater than 100, then the Frequentist is going to set up a null hypothesis that contradicts that and says that the mean is equal to 100, then going to calculate the probability of getting the observed data. In contrast, what the Bayesian does is they fix the data, and then they're going to obtain the posterior distribution of mu conditional upon those data. Some additional calculations. So, the Frequentist knows with absolute certainty that if the IQ of IB students is normally distributed with mean 100, and that's our null hypothesis, with standard deviation 15, that was our assumption up here, then if we took all possible means based on a sample size of 9, those means, we represent those as y bar, those are going to be normally distributed with mean 100 and standard deviation sigma over root n, which is going to give us 5. What the Bayesian is going to do is a series of calculations in RunJags. And so we're going to need to have a prior, and this is our prior, that mu is going to have a flat prior with a standard deviation here of 100. And we're going to specify a mean of 115, but given the high standard deviation, it doesn't really matter what we specify as our mean. It's going to get about the same answer. Here is our likelihood function. The data are kept constant at these values here, and those are assumed to arise as random draws from a normal distribution with mean mu. That's what we're interested in, and precision 1 over 25. Again, standard deviation is 15. 1 over 15 squared gives us 1 over 225. Then we're also going to have this derived value of prob using the step function. And the way that that's going to work, is that if mu is greater than 100, prob is going to be equal to 0. And if mu is less than or equal to 100, then prob is going to be equal to 1. Okay. Next thing that the frequentist does is that frequentist knows that sample means based on a sample size of 9 are going to be normally distributed with these features if the null hypothesis is true. So this is the sampling distribution. This is a distribution of all means of sample size 9 taken from this distribution. So there's the data that we observed. We observed a mean of 111. So if we come back here, what we can say is if the null hypothesis was true, if the mean was actually 100, what's the probability of observing a mean of 111 or more? And we can calculate that by using some R code. What's the probability of getting a mean of 111 or more, given the mean was equal to 100? That was our null hypothesis. Given the standard deviation of 5, that was our calculated here. And we're going to use lower tail, because this is the upper tail. We really need the lower tail. What we get is a value of 0.01393. So what this means is that if our null hypothesis was true, the probability of observing the data that we got has a very low probability. That serves as evidence that the null hypothesis was false. The null hypothesis was false, and that serves as evidence that the research hypothesis was true. So what the Bayesian can do is the Bayesian is going to come over here, and they're going to plot results. And we're going to look at these two parameters. Look at mu and look at prob. And the whole idea is that as JAGS goes on its random walk, it's going to come up with 60,000 values of mu and prob, and it's going to produce these histograms with plot results. So there's our 60,000 values of mu presented as a histogram. And here are our 60,000 values of prob. They can be a 1 or a 0. And what you can see is the vast majority of these are zeros. So the vast majority of these are zeros where the probability, mu was greater than 100. There's only a few values of 1. There's only a few values where mu was less than 100. And in fact, we can do the statistics on both mu and prob, get the mean of those two, and the mean value of mu was 111, which is the data that we observed, and this is a really key thing. This value, prob. To make things simple, I'm just going to have this equal 1.4%. So what we're saying is that 1.4% of the time, 1.4% of the time, we got ones. Ones were the mean less than or equal to 100. 98.6% of the times, we got zeros, which was mu greater than 100. So the value here of 0.0139 and the value here of 0.1393 are telling the same story, but they're telling it in very different ways. So what the frequentist is doing is they're holding the parameter constant at 100, and they're calculating the probability of data as similar to that observed or more extreme. Whereas in contrast, what the Bayesian is doing is they're holding the data constant, they're getting the posterior distribution of mu, and then if you think about what's happening here, think about what this value means, we've got 0.0139 is the proportion of values that are less than 100. What the Bayesian is doing is calculating the probability of the mu conditional upon the data. Now what I want to do is go over some of the advantages of using the Bayesian approach. And again, remember that a number of these advantages are really comparing the Frequentist P value with the Bayesian posterior, as opposed to a general comparison between Frequentist and Bayesian methods. But we can see, at least in this case, that the Bayesian is more direct and intuitive. So here we have a list of things that the Frequentist does. The Frequentist begins with a research hypothesis that the IQ of the IB students is greater than 100. Then they set up a null hypothesis that contradicts this and says that, okay, instead of being greater than 100, the mean IQ of the IB students is equal to 100. Then they calculate the conditional probability of the data conditional upon the null hypothesis, and the data was an average of 111 based on a sample size of 9, and we know that the probability of getting a mean of 111 or more, and given a sample size of 9, if the null hypothesis is true, is only a very small number, 0.01393. That is the p-value. Because this is a small number, that small number is strong evidence that the null hypothesis is wrong, and that in turn serves as strong evidence that the research hypothesis, which is contradicted by the null hypothesis, is in fact correct. Whereas the Bayesian provides a very direct answer, far more direct, far more intuitive. It just tells us, okay, here's our histogram of mu, and here is 100 value here, that the probability of the mean IQ of the IB students being less than 100 is only 0.01393. The Bayesian posterior provides additional information that the frequentist doesn't. So all we get from the frequentist is, in this particular example, there's a very low probability that our null hypothesis is true. That provides strong evidence that our research hypothesis is correct. But it doesn't tell us anything about effect size. Whereas in contrast, we can look at the posterior and we can see, everything we possibly want to know. For example, we could see that, the vast majority of these, very likely, very probable, that mu lies somewhere between, let's say, 106 and 116, looking at this plot. We also, and this is not so relevant here, because here we have a normal distribution, but there may be instances in which we have a skewed distribution of our parameter of interest. And knowing that we have a skewed distribution is something if it does show up, is something that we ought to embrace and take that as being something very useful to know. A third feature is that the p-values may overstate the evidence that supports the research hypothesis. So to demonstrate that, let's consider an example where what we're trying to do is we're going to try to examine many treatments, maybe drug treatments or reclamation treatments or something like that, and we're trying to identify those that are effective, but we know in advance that probably, this is particularly true of drug screening trials, where most of the treatments won't work. And so what I've set up here is HO is the null hypothesis, and HO plus, this whole thing here, is the state that the null hypothesis is true. So that's what this HO plus means. The null hypothesis is true, and that means that the treatment has no effect. Now we're going to look at Bayes' theorem, of course, and we're going to take this thing HO plus, and we're going to substitute it for theta. So we're going to substitute it there, 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 there. And what do we have here? What's this going to be? This is going to be the prior prob. The null hypothesis is true. The prior probability of no useful effect, or we'll just call it no effect. And what we have here is the posterior probability of no effect. And what's this thing? This thing, of course, is our p-value. And the whole idea is that in a screening trial, where most of the treatments aren't going to work, the prior probability of no effect is going to be a large number. The whole point is that even if we get a p-value, which implies to us that, in fact, we are having a treatment effect, even a small p-value, if this is a large number, is actually going to be a situation where the posterior probability of no effect is going to be quite large. So the whole idea here is that by relying on this thing as opposed to this thing, in scenarios in which there's a very high probability that our treatment is not going to be effective. This small p-value may overstate our confidence that our treatment is actually working. Now, this whole idea about p-values and whether or not it overstates the evidence, that's really complicated. And on E-Class, there's a supplementary materials that focuses on p-values, and it's called A Trip Down the Rabbit Hole because it really is nasty complicated. If you want some more details, you can look at that special topics. Actually, it's not a supplementary material, it's a special topic. The reason I bring it up is that there's a very important paper by John Ioannidis, talks about why most published research findings are false. It's been cited about, last time I looked, about 6,200 times, and part of his reason that he argues that most of our published research findings are in fact false is based on this logic. In practice, however, I don't know how important this phenomenon is. The fact that in screening studies, p-values may overstate our confidence in a treatment that's effective. Because I think we already know that. I think we should already realize that using p-values in a screening study is not a really good idea unless you put in some sort of a correction for the fact that there are a large number of treatments that are being tested.